Hello, and welcome to this introductory video on wave properties. In this video, we're going to take a quick look at the key properties that help us to define and mathematically describe waves. So when we think about waves, we know that there's this oscillatory motion. The wave seems to be doing some sort of nice sinusoidal variation. It's got some sort of height to it. It's got some sort of width. The particles themselves are jiggling around. We would like to characterize all of that and be able to describe it mathematically. To do that, we need to define some convenient parameters. So if we think about that, there is one really obvious one. What is the height going from the axis up to that peak, or equivalently from the axis down to there? What is that distance, the maximum distance I get from the axis? We call that the amplitude. And as I said, that describes the height of this wave. The next key parameter is what we're going to call the wavelength lambda. And that has to do with sort of the width of this thing. Rather than just be the width of sort of the base of a peak, what we do is we define it to be from peak to peak, i.e. the time it takes for the wave to complete one sort of full cycle. It goes away from where it was and it ends up back again where it was. So we start at a maximum, we go to a minimum, and then we go to a maximum again. That full cycle, the distance over which that occurs, is what we call the wavelength, and that's what we define really as the width of this thing, peak to peak. Okay, when you have that description, then you can talk about this displacement of each particle along this x-axis. So if I'm sitting here, particle normally would sit here. How far do I move along x? So I can talk about this big x of x, and it's coming from this thing. And it's just going to be the amplitude, because that sets the height at which I'm oscillating, and times this cosine factor actually. So we said sinusoidal variation, but in common practice we start off with a cosine to describe that wave. Okay, and we'll give it as a 2 pi on lambda times x. So then, what else can we do? Well, obviously this wave was moving along, so if I followed one peak that was moving to the right at some rate, I can think about that rate as the wave speed. So the speed at which this wave is actually propagating, we're going to call that v sub w, using the notation of the textbook. And then this is just talking, as I said, the rate at which the wave is moving. Now, we realize since it's moving that things are actually changing in time as well. So let's say I pick a particular x, and I would like to know, sitting here, of course, if I watch the wave move by, well, this particle sometimes is displaced to the left and sometimes to the right. How long does it take, say, to start here and go all the way to the left, all the way to the right, and back again? Or, equivalently, how long does it really take for me to travel one whole wavelength? That is what the period is describing, the time to complete one cycle of getting back to where I started from in this sort of oscillatory motion. Okay, so, for example, time taken to go from peak to peak at its current location, or at some particular location that you choose. All right. Now, when you think about a time variation, then you can talk about a similar sort of function, that the current displacement in time, if you will, at the particular location, the displacement as a function of time, is given by the amplitude again, that's the maximum displacement I could ever have, times cosine of 2 pi divided by t times t. Okay, and that therefore varies from 1 down to -1 and back to 1 over a time scale t, just like the previous one actually varies from 1 to -1 and back to 1 over a distance scale of lambda, because cosine varies over a factor from 0 to 2 pi. That is how cosine completes that 1 to -1 and back to 1 again. So if we make x lambda, we see we get back to 2 pi. So we have completed a cycle, and similarly for the times. All right, so that's sort of a nice description there, but what else can we do? So let's take a look. This was what we wrote down for our time description. Now I can introduce some additional things. One on the period is the frequency. It took me a time equal to the period to complete one cycle. So if I divide 1 by that time, then what I end up with is the cycles per second, which is exactly what a frequency describes. And then I can take it one step further. I can do something like this, which is just say I'll multiply that factor of 2 pi that would be sitting in our expression anyway into the f. That takes me from cycles per second to basically radians per second, because one full cycle is indeed 2 pi radians. So now I've got radians per second. That is my angular frequency. How quickly do I move through the angles to get around that cycle? And then I can do similar sort of manipulation. So I can look at my spatial dependence, the displacement as a function of position, and I can take this 2 pi on lambda and just rewrite that to be a constant k, which we can talk about as a wave number that describes this thing, this wave. Now I can do something a bit more clever. I've got a description for how it varies in time and in space, so I can combine them. I can just grab the kx from the spatial part and the omega t from my time variation and put them together right there. This is exactly the same sort of thing. It's got an overall amplitude of x. It's varying now in space and time at the same time. And then we realize, if we think back to the plot that we had earlier, that the cosine was actually starting at 0, which is not true for cosine. If x was 0 in an earlier plot, then we realize that that's not really a description of what that function looks like. So we can add in some arbitrary phase constant, phi naught. So that phi naught is just a phase constant, pi on 2 or whatever it needs to be to shift the cosine so it actually matches our plot over here. And then we can summarize all of that by just saying that really all of this is just giving rise to some angle that's going to be between 0 and 2 pi basically for the cosine to operate on. We can just call that whole thing the phase of our wave. And it's a time varying phase and a space varying phase. So we've got our sort of general form. How fast is the wave going? Well, remember that's the wave speed. And the wave speed is given by the distance that the wave will travel divided by the time. Well, that is the wavelength. That's the total distance. It travels that in one period. So we can write it as lambda on t. But 1 on t is just the frequency, so we can write down that v wave is just f times lambda. Okay, and I invite you to think about how fast any particular particle in this wave is jiggling the left and right.